In this video, we look at some of the theoretical considerations and practical experimental factors that we can use to control or affect the rates of chemical reactions. The fundamental underlying differences in the rate of reaction for different chemical processes lie in the chemical nature of the reactants themselves. During chemical reactions, bonds are typically broken and new bonds are formed. Some chemical reactions are by nature very slow, for example, the chemical degradation of plastic. And some are very fast, for example, the combustion of methane. It is the inherent tendencies of the substances in these reactions to undergo bond breaking and bond forming processes that result in different rates of reactions for different chemical reactions. At the molecular level, reaction rates depend on the interaction of reactants and, in particular, the nature of the collisions between the reactant particles, including the frequency of collisions between the reactants involved, as well as the orientation of the collisions and the energy of those collisions. If we can increase the frequency of collisions with the correct orientation and with sufficient energy to allow the breaking and reforming of bonds, this will result in increased rates of reaction. In terms of frequency of collisions, reaction rates are maximized when we maximize the rate of collisions between reactant particles, and we have a couple of experimental variables that we can control. For example, if we start with a relatively low reactant concentration or a relatively low temperature, we are likely to have relatively low collision rates and therefore relatively low reaction rates. On the other hand, if we start with a relatively high reactant concentration or a relatively high temperature, we are likely to have relatively high collision rates and therefore relatively high reaction rates. In terms of the orientation of collisions of reactant particles, it turns out that most collision between reactant species are actually ineffective and do not lead to the formation of products. This is because even if the reactant particles come together with enough energy, they are typically not oriented correctly to allow stretching and breaking of existing bonds and forming of new bonds. For example, let's consider the decomposition reaction of nitrosyl chloride to produce nitric oxide and elemental chlorine, which can be represented via this chemical equation or via these space-filling models of the reactants and products involved. If the reactant molecules collide at this orientation, where there is limited opportunity to form the required bonds between the two chlorine atoms, then there is little chance of an effective collision leading to product formation. Similarly, if the reactant molecules collide in this orientation, there is also limited opportunity for the appropriate bond breaking and bond forming. If, however, the reactant molecules collide with this orientation, there is much greater likelihood of breaking the nitrogen-chlorine bonds and forming the chlorine-chlorine bond, and therefore a much greater likelihood of the reaction proceeding. The energy of reactant particles and the energy of collisions is also an important consideration. For example, in the electrophilic substitution reaction between bromomethane and the hydroxide ion, the reactant species need to come together not only at the correct orientation for bond breaking and bond forming, but also with the right amount of energy to stretch and ultimately break existing bonds so that new bonds can be formed. The amount of energy needed to allow a reaction to proceed to any significant extent is called the activation energy, EA. If the energy of the reacting substances is low relative to the activation energy, then the rate of reaction will be slow and the reaction will not proceed to any significant extent. Experimental factors that can be controlled to ensure there is enough energy to overcome the activation energy include temperature. The higher the temperature, the greater the energy of the reactant species, and the use of a catalyst, which acts to lower the activation energy of the chemical reactions and therefore greatly speed up the rates of chemical reactions at certain temperatures. There are at least 4 general experimentally controllable factors that we can alter to affect rates of chemical reactions. The first involves the physical nature of the reactants. Most chemical reactions involve 2 or more reactants which must physically mix in order for the reaction to proceed. The more readily reactants physically mix and intermingle, the greater the rate of reaction. It is for this reason that chemical reactions are rarely carried out purely in a solid state. Most of the reactions that we consider are homogeneous reactions that take place in a single visible phase, and usually in either the gaseous state or the liquid state, via reactants dissolved in solution. When reactants occur in different states, or even in different phases of the same state, we say that the chemical reaction is a heterogeneous reaction. In heterogeneous reactions, the chemical reaction is limited to the contact area between the two phases. For example, the chemical reaction between reactants dissolved in two different liquid phases would be limited to the contact area between these two phases, and it would be normal practice to thoroughly shake a reaction mixture in a separating funnel such as this to ensure that we maximize the contact between the two reactant phases, and therefore maximizing the rate of reaction. Likewise, the heterogeneous reaction between solid iron, Fe, and oxygen gas, O2, in the formation of rust, Fe2O3, is a heterogeneous reaction that is limited to the surface of the solid iron. Lack of mixing and limited contact between the oxygen gas molecules and solid iron atoms below the surface limits the frequency of collisions and therefore limits the overall rate of this redox process. Another experimental variable that we can control relating to the physical nature of the reactants is the surface area of solids in a heterogeneous reaction. For example, if we were to physically pulverize an iron sample, its surface area would be considerably increased, thereby increasing collision frequency and thus the rate of this rust-producing redox reaction. Along similar lines, a 5 kilogram piece of wood in the form of a log or a piece of timber would take considerably longer to burn than if we were to burn 5 kilograms of sawdust. The increased surface area of sawdust would allow greater contact between reactants and therefore an increased rate of reaction. The second general experimental variable that we can control is the concentration of reactants. Most chemical reactions, whether homogeneous or heterogeneous, proceed faster if the concentration of one or more of the reactants is increased, and we deal with the quantitative relationship between concentration and rate of reaction in subsequent videos. For now, we can consider the difference in combustion reactions which occur in air and combustion reactions that occur in pure oxygen. Combustion reactions in air, which contains about 21% oxygen, can proceed readily enough at quite rapid rates. But they generally occur much more readily and give off much more energy in a shorter period of time if they are carried out in the presence of pure oxygen. In this case, the frequency of collision between the reactants is increased by increasing the oxygen concentration, thereby increasing the rate of reaction. A third experimental variable that is readily controlled is temperature. The rates of most chemical reactions increase as we increase the temperature. This is why we place dairy products in the refrigerator. The biochemical reactions of bacteria that lead to the spoiling of milk occur at a slower rate at lower temperatures. Increasing the temperature of a reaction mixture increases the energy of the molecules involved, thereby increasing the vibrational, rotational, and translational motion of molecules. This in turn increases collision frequency and provides more opportunity for molecules to collide at the correct orientation with sufficient energy. A general rule of thumb is that the rate of chemical reactions will roughly double for every 10 degrees Celsius rise in temperature. The final experimental variable that we can readily control to affect the rates of chemical reactions is the amount and presence of a catalyst. A catalyst is a substance that increases the rate of a chemical reaction without itself being consumed in the chemical reaction. Catalysts alter the nature of collisions between reactant molecules via a range of mechanisms, resulting in a lowering of the activation energy required for a reaction to proceed. This means that for a given set of reactant concentrations, a catalyst will increase the rate of reaction without the need to increase temperature. Catalysts play a crucial role in countless industrial processes, including chemical synthesis, and play a crucial role in living organisms. For example, the enzymes that govern our physiology are catalysts which speed up the rates of crucial reactions in all major biochemical pathways. We can use the example of the combustion of glucose in the presence of oxygen to produce carbon dioxide and water as an example. This energy diagram shows that to perform this reaction in the laboratory, we would need to add a lot of energy, for example by igniting a sample with a flame, just to kickstart the reaction. In other words, we would need to overcome the activation energy barrier to set up the right conditions for bond stretching, bond breaking, and ultimately new bond formation. This same overall reaction occurs in our bodies when we break down glucose to form carbon dioxide and water during respiration. Through a series of enzyme-catalyzed reactions, we can see that the activation energy can be significantly reduced such that the reaction proceeds well enough and at a good rate at body temperature, much less than would be required in the laboratory when we burn a sample of glucose via conventional combustion processes.